The function f is defined on the closed interval from -2 to 8 and satisfies f of 2 equals 1. The graph of f prime, the derivative of f, is shown here and consists of two line segments and a semicircle. At x equals 6, does f have a relative minimum, a relative maximum, or neither? To find this out, we will use the first derivative test. Setting up a number line for x at equals 6. For f prime, we are testing the sign of the first derivative. To the left of x equals 6, it's positive. And to the right of x equals 6, f prime is still positive. Therefore, no sign change has taken place for f prime. And that means that there is neither a relative minimum nor a relative maximum at x equals 6. Next, on what open intervals, if any, is the graph of f concave down? Well, f is concave down if its second derivative is negative. And if its second derivative is negative, that means the first derivative will be decreasing. So we must look at the graph to find where f prime is decreasing. And we see that it is decreasing here, as well as here. That is, on the open intervals from -2 to 0, and from 4 to 6. So we put the union of these two intervals as the open intervals for which the graph is concave down. Next is to find the value of the limit as x approaches 2 of 6f of x minus 3x over x squared minus 5x plus 6. We first tried direct substitution to see what this gives us. By plugging in x equals 2, and evaluating both the top and the bottom of that fraction. Noting that f of 2 is equal to 1, we get 0 over 0, an indeterminate form, which is the perfect time to use something called L'Hopital's rule. And L'Hopital's rule will have us take the derivative of the top of that fraction, as well as the derivative of the bottom of that fraction, and then try direct substitution to evaluate the limit. So that'll look like the limit as x approaches 2 of 6f prime of x minus 3 over 2x minus 5. And by direct substitution here, we get -3 over -1, or positive 3, as the limit. The last part is to find the absolute minimum of the value of f of x on the closed interval from -2 to 8. And we must note that the absolute minimum is also a relative minimum. So f prime equal to 0 will tell us where the relative minimums exist. So the candidates for our minimums are where x is equal to -1, positive 2, or positive 6. That's where f prime is equal to 0. Now we've already noted that at x equals 6, we have neither a minimum nor a maximum, so that is not our absolute minimum. We can cross it off our list. For the other two candidates, we use the first derivative test again, testing the sign of the first derivative along this interval. At x equals -1, we'll get a maximum, and at x equals 2, we'll get a minimum, so we can cross -1 as x value off our list. And now all we have to do is use x equals 2 to test, as well as the endpoints of our interval, -2 and positive 8. So let's set up a table of values here. Now we're going to use the definite integral definition to help us evaluate f of x. And the integral from 2 to x of f prime of t dt is equal to f of x minus f of 2. And that's by the fundamental theorem of calculus. So rewriting this equation, we get f of x is equal to the integral from 2 to x of f prime t dt plus f of 2. Now since we know f of 2 is equal to 1, we can replace f of 2 with 1. So now we have a way of evaluating f of x at different x values. And that's what we'll go to do, fill in this table of values, and find out which one is the minimum. So starting with -2, f of negative 2 is the integral from 2 to negative 2 of f prime t dt plus 1. And what we'll do here is we'll swap the limits of integration here, picking up a negative sign in doing so. Now the integral from negative 2 to 2 is the area under the curve. So we'll be calculating the area under the curve by using the graph here from negative 2 to 2. And it looks like we're calculating the area of a few triangles. Now from negative 2 to 0, those two areas will cancel each other out because we have signed area to think about here, and the other triangle will be negative 2. So our total integral here will be negative negative 2 plus 1, which will work out to be the value of 3. So f of negative 2 is equal to 3. Next, f of 2. Now we do know that f of 2 is equal to 1, but let's see why using this definition. When we integrate on the same limits of integration, that always equals 0. And so we just get 1 here. And finally, at x equals 8, we get the integral from 2 to 8 of f prime t dt plus 1. And that's going to require us to think about that semicircular area. So we'll block things off. We have that triangular area to the left. And the area that we want right here is underneath that semicircular area, or curve I should say. And then what we're going to do is we're going to block off the area for the triangle here, as well as put a rectangle around the area of that semicircular arc. So by putting a rectangle in here, we note that the area of that semicircular arc, a circle of radius 2, will have an area of 2 pi. And the area of that rectangle works out to be 4 by 2, which is 8. And together with that triangle off to the left, and what we're going to do is we're going to subtract away that semicircular area, what we're left with altogether is 10 minus 2 pi. And that, as a decimal value, is approximately equal to 3.7168, etc. So now, comparing the values in our table, we see that at x equals 2, we get the smallest y value, our f of x value, is equal to 1, our absolute minimum on the interval from negative 2 to 8. So f of 2 equal to 1 is our absolute minimum on negative 2 to 8. And that's the last part of question number 4, the free response question in the AP Calculus 2023 exam. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.